All right, so we have another problem here. We have a child sliding down a slide. We're assuming they're starting at rest, or I guess not assuming, the problem tells us that. They're telling us the length of the slide. So I'm going to go ahead and just kind of represent this in a picture. Length of the slide, how long it takes to get to the bottom. Having a distance in time here should give me the thought of kinematic equations, or the big three. The slide is inclined at an angle of 25 degrees with the horizontal. We're looking for the coefficient of kinetic friction. That's that mu sub k. And that's related to the force of friction. The force of friction on the child will be this coefficient times the normal force that the child is experiencing. So kinematic equations, knowing the child starts at rest, we know the distance the child is traveling, we know the time. That information from the previous section we can calculate for an acceleration. So if we were to set up that table of information, now why I'm solving for the acceleration is because I know, according to Newton's second law, the acceleration the child experiences is determined by the force, it's caused by the force, and then inversely related to the mass. So to relate the forces in the problem, which to get to coefficient of kinetic friction, we need to be able to talk about the force of kinetic friction. So to relate the motion to the forces, I need the acceleration. So that's why I'm jumping to this point. If I say the initial position is 0, the final position is 5.5 meters. I know the child starts at rest. The problem tells me that specifically. I know the time. I need acceleration in order to relate this information to the forces. So in terms of kinematic equations that has S initial, S final, time, and acceleration, that's that, I think it was the second one. So we're saying the child starts at rest and calling the initial position the 0. So let's see, I can solve for A. So 2 times this 5.5 over the time squared. This will give me the value of the acceleration. So 2.494. Again, keep more digits than we're going to end up rounding to at the end. This acceleration, I hope it's fairly obvious to us. This acceleration is going to point down the incline. To make the algebra on this problem easier, when I go to write the equation describing forces at any given moment in time, I know the child will be moving down the incline. So I'm going to go ahead and make the x-coordinate parallel to the incline and the y-coordinate perpendicular. By choosing this coordinate system, this acceleration is all in the x direction. So this acceleration we have calculated is all in the x direction, and the acceleration in the y direction is 0. But that's specific to this coordinate system that I have chosen. But that's okay. We can choose any coordinate system we want as long as we maintain the correct signs, directions, as we set up the equations. So it actually is nice to be able to say the acceleration is all in one direction. Now, to relate this back to forces, we totally want a free body diagram. Just going to draw that over here at the left. Force of gravity, we know, points straight down. Force of gravity always points towards the center of the earth. The normal force is always perpendicular to the incline. So if I was drawing that coordinate system in that I drew to the right on the slide, the normal force is in the y direction that I drew. Again, the word normal, the term normal, means perpendicular to the surface. One other force, with this child being in contact with the slide, there's some friction. The other inclination or indication that exists, of course, is because it's asking us for the coefficient of friction. So there has to be a force of friction. The force of kinetic friction is always opposite the motion. So since this child is sliding down the incline, I would draw the force of kinetic friction pointing up the incline. So another benefit to rotating the coordinate system, making the x-axis along the incline, is that now in this new coordinate system, the normal force is all in the y direction. The friction force is all in the negative x direction. So we only have to break down mg into its components. So the x component of mg has to be parallel to the x-axis. The y component has to be parallel to or along the y-axis. So they have to meet at that right angle that I've drawn. Now, the reason I'm drawing my triangle on that side, just as a reminder, my original typical Cartesian coordinate system, I've rotated it by 25 degrees in this case, the angle of the incline, to get this new x-axis. But that means the y-axis rotated by 25 degrees to get our new y-axis. So this original y-axis rotated by 25 degrees. That means in my free body diagram, the angle between mg that I've drawn, the force, and that y component is 25 degrees. That's always the case when we rotate our coordinate system. So this side will be mg cosine 25. This side will be mg sine 25. So now let's go ahead and write out what we mean. I'm going to go ahead and write our net force equals ma. But we need to do so for the x direction and y direction specifically. And again, the x direction being parallel to the incline and y being perpendicular to the incline. So the net force, the forces acting specifically in the x direction. We have the force of friction pointing up the incline, so I would say minus the force of kinetic friction, because that's in the negative direction according to the coordinate system I have chosen. And then gravity, this x component, whether I draw it down there or up here, that points down the incline, so that's my positive direction. And the component of gravity that points down the incline is that mg sine 25. So this represents all of the forces in the x direction. So net force x. That must equal the mass of this child times the acceleration of the child in the x direction, which we have already calculated. We know this value. So we always want to write out our equation symbolically. Let's keep going and look at the y direction as well. Now, by the way, Typically, around this point, students start worrying that they have not been given the mass of the child. Ignore that for a minute. Just keep plugging through, keep getting these equations written up and substituting things as possible. And we're going to see the mass will cancel out. But we need to show that. We can't just not write mass. We have to actually show that it cancels. All right, so the forces in the y direction, because of the coordinate system we've chosen, there's no acceleration in that y direction. So the forces in this y direction in our free body diagram, they must balance out. We've chosen this coordinate system such that now we know the acceleration is 0. What that tells me is the normal force in the positive y direction must balance out with the component of gravity, the mg cosine 25, in the negative y direction in my picture. So right now, not having been given the mass, we don't have enough information to calculate the force of friction yet. But that's okay. Just keep writing these symbolic equations. What we're going to do now is, because the force of friction, how big the force of friction is, depends upon the coefficient of friction and the normal force, I'm going to come to my x equation and I'm going to put that in. Now you might see a jump we could have taken. I now know the normal force in terms of mass, so I'm going to plug that in for normal force. Typically, I would have plugged that in and not taken this individual step of mu times n, simply because I've done this enough times. But I wanted to show you these steps we're taking. All right, so I have my original F equals ma for the x. So net force in the x direction is equal to mass times acceleration in the x direction. Net force in the y direction has to be 0 because we've chosen a coordinate system where y is perpendicular to the incline. And from there, I start substituting in any relations that I know, like the force of friction depends upon the coefficient in the normal force, and so forth. It's at this step, if I divide every term by m, the mass is canceling out. So we do not actually need to know the mass of this child to calculate the answer. So this is another reason why it's nice to go ahead and just write things out symbolically, not worrying about the numbers you've been given yet. So here we know this acceleration in the x direction. That's what we calculated originally. We know g, and so we can actually, our only unknown is that mu. So I'm going to bring the mu g cosine 25 to the other side just to make it positive. That leaves me with g sine 25, and then bringing the acceleration over. Then I can divide by g cosine 25 to solve for mu. So g we know is 9.8. We've already accounted for the direction of the force of gravity, so g is always just positive, 9.8. It's the absolute value or magnitude. So plugging these values in, I'm getting 0.1855 units. G has units of meters per second squared. Our acceleration has units of meters per second squared. So we're getting meters per second squared over meters per second squared. So there are no units, which you might have remembered that from talking before. Now, significant figures, coming back to the problem, 5.5 is 2, 2.1 is 2 sig figs, 25 degrees is 2 sig figs. So I would want to round this to 2 significant figures. 0.19. If you remember, the coefficient of kinetic friction is typically between 0 and 1. 0 would mean none, no kinetic friction. 1 would be a whole heck of a lot of kinetic friction. This seems pretty reasonable. Being closer to 0, the child can slide down the slide fairly easily, but not as fast as if the slide was perfectly frictionless. So this answer seems reasonable. So again, the process is the same. Free body diagram, write out F equals ma for x and y. It might be, if you had written these equations out first, you would have realized you need acceleration, and then hopefully would have realized you can use this other information to use the big three or the kinematic equations to solve for that acceleration. So the process, practicing the process is really important. Don't rely on final solutions. For example, don't memorize something like this where mu ends up being g sine 25 minus a over g cosine 25. It defeats the purpose, and actually we can't guarantee that that equation is applicable for anything on an incline. So the process, the approach to the problems is always the same, and that's what we want to practice.